Okay, so we're getting into a main topic, which is limits in calculus. And so there's different ways to look at limits. And I think the first way to look at it, if we look at it geometrically first, that'll give you intuitively what's going on. And then we'll look at solving them algebraically, and I'll give you tools on how to do that. Basically, what this is going to say is we're going to have some graph. Let's just choose some value, x, on the graph, and I'm just going to call this value right here a. And so let's look at a graph. And what we're trying to determine is what is going on at this value x equals a when we get really, really close to it. So we're looking at getting close to this. We want to know what's happening on the graph. What y value are you getting close to as you're getting closer and closer, arbitrarily close to this value a, but not necessarily this value a. So from over here at this point, or where it looks like it, let's say that this y value, let's say this value is called capital L. And so limit as x approaches gets really, really close to some value x equals a, then what is happening to the graph at that value? What y value do you approach? If any. So it's possible it doesn't go to any particular y value at a graph, and I'll talk about that in probably more tomorrow. Notation on how we would write this. If we're looking at limits, it's LIM, short for limit. Underneath the LIM, and normally I do that in cursive, you're going to do your x value or whatever variable you're looking at. Like our last example, we were talking about time, so we would have used t there for the horizontal axis. But x is approaching a of whatever your function is called here. So maybe this function is called f of x. It could be called g of x. This is equal to L. So in our case, that limit, as we got closer and closer, so I kind of go to the left. And when we're looking at limits, we actually need to show that the limit as we're approaching on the left-hand side of that graph is the same y value as we're approaching on the right-hand side of the graph. And so this is where a little bit more notation comes in to determine what side you're coming in, or show, or by notating what side you're looking at. So if I was looking at the limit, or I was looking at this piece of the graph of what's happening on the left of x equals a, I would denote that with the notation as the limit, LIM. Underneath, x is approaching a. But to notate that I'm coming in on the left, I'm going to put this, what looks like a exponent of a negative, or a superscript of a negative, of f of x. In this case, this is also, when I'm coming in on the left, the y value that I'm getting closer and closer to is L. So how I would notate that I'm showing that I'm coming actually in on the right-hand side of A and getting closer and closer to A on the right-hand side. So I'd go up to the graph to the right of it, that point, and the limit as x approaches A on the right, so put a superscript of a plus sign, f of x is equal to L. So in order for this to exist, a limit to exist, both the left-hand side limit has to be the same as our right-hand side limit. So note, in order for a limit to exist, the limit on the left has to equal the limit on the right. So maybe if you're showing work that a limit doesn't exist or a limit does exist, show that your left-hand side is equal to your right-hand side. Okay, so there's a few things that you have to be aware of when we're looking at limits. Something might actually not be defined at that x value, but it's on the graph. It has some behavior there. So for instance, going back to rational functions, recall that when you were graphing rational functions, you found asymptotes. And you found those if there were values that set the denominator equal to 0, but not also the numerator. And so if I look at this function, f of x equals x squared minus 1 all over x minus 1, I know it's undefined on values that my denominator is equal to 0. So I know that for my domain, it's all real numbers except x equals 1. So shorthand for real numbers really is just the capital R, but with two vertical kind of parallel lines there. So real numbers except x can't be 1. But graphically, if you looked at f of x and we simplified it, we factored our numerator. So let's look at this. F of x is equal to, well, this is a difference of squares, x squared minus 1, and I see that factors as x minus 1, x plus 1, all over my denominator of x minus 1. So before you find, you simplify like factors in the numerator denominator, this is where you really should look at your domain. If I cancel this, x minus 1, my original function, f of x, still x can't be 1. If I look though, and I go back in and I plug in 1 where I see an x after I simplified it, notice that I would get 1 plus 1 here, which is 2. So let's go up to the graph there. So this is basically saying my graph of f of x equals x squared minus 1 all over x minus 1 looks like the same graph as x plus 1, but there's a hole at x is 1, y is 2. So that's why we get this graph right here. But what's happening here, if we look at the limit as x is approaching 1 on the right and the left. So let's look at the limit as x approaches 1. this part A, of f of x. Let's look at the left-hand side first. So whenever I'm looking at limits of a graph, I always look at the x value that we're looking at, which is 1 in this case. I go up to where my graph is from that x value. I'm looking on the left of it. Sometimes you have more than one piece of a graph. This time we only have one graph. So it's just here. And so as we get closer and closer to x equals 1, the y value you're getting closer and closer to, even though it's not 2, is 2, right? If I get to 0.9 here, I might get 1.9. If I get to 0.99999 here, I might get 1.9999999. And so as we get closer on the left to x equals 1, we're getting a y value of 2. And if we approach here on the right, as x gets closer and closer to 1, we're getting a y value of 2. And since the limit of the left and the right are the same, that means the limit exists. So the limit as x approaches 1, just in general of f of x, is equal to 2. All three of these cases, and then I know I'm running out of time, I'm out of time, so let me just really quickly say it. All three of these examples, they almost look identically with a graph. And if we look at x equals 1 on each one of these cases, when we're coming in on the left and the right, we're getting the same y value, even though it doesn't exist here, we're getting 2. Or notice that g of 1 in this case, there is actually a point here. When x is 1, this piecewise function tells me my y value is 1. And here, the limit as x gets closer and closer to 1, this point actually exists, and it is equal to 2. Okay, so there is a really quick introduction to limits and what they mean geometrically. And so we'll get into some examples of these tomorrow. Okay. Any questions?